everybody. So today I want to talk about the evolution of efficient and robust AutoML systems. Just a quick note, the slides are available at automl.org/talks. So to get started, let me talk about traditional machine learning and AutoML. So in traditional machine learning practice, you have the data coming into, well, the machine learning expert, and the machine learning expert needs to choose architecture and hyperparameters, and then uses the learning box in order to actually learn some model. And typically, unfortunately, that is not a one-stop process, but rather after having done this once, the machine learning expert needs to choose different architectures and different hyperparameters until the performance is as good as they wish. In AutoML, we want to turn this around and rather go towards end-to-end learning. In comes the data, and then the system actually does the learning. After all, it's called machine learning. It's not called human experts learn about which architectures and hyperparameters perform well. And if you have such a system, then you can actually, of course, also bake in different objectives. You can bake in explainability or interpretability or fairness or robustness or any objective function that you actually want to optimize. And then AutoML should be tasked in order to come up with methods and models that satisfy those desiderata. So how can we actually get towards end-to-end learning? Well, one way of doing that is actually just to mimic this machine learning expert here, what they do, by actually having this meta-level learning and optimization process that learns about the performance of this learning box. And yeah, then you can try different architectures, different hyperparameters, and so on, and learn about how well they do. You can learn across data sets, et cetera, and actually build up the intuition that machine learners build up manually in an automated fashion and do machine learning on top of that. Now, a quick note, AutoML is a broad field by now. In particular, there's sort of two subfields. There's neural architecture search and more like automated data science. And neural architecture search is a really exciting field, but it's not yet at the majority level of AutoML systems. And this talk here focuses more on AutoML systems and in particular for tabular data because those are the most mature. In particular, I will briefly mention our first AutoML systems, Auto-WEKA and Auto-sklearn, but then I will focus on our current AutoML systems, Auto-sklearn 2 and Auto-PyTorch Tabular. This work is in collaboration with my PhD students, Matthias Feurer and Katharina Eckensberger, with Lukas Zimmer also for Auto-PyTorch Tabular, and with my previous postdoc and now collaborating professor, Marius Lindauer. I will also have at least 2 slides on sort of the future of where Auto-PyTorch Tabular is going, in particular in using all kinds of different regularization in there in order to get yet much better performance. And that is work together with a PhD student, Alan Kadra, and a collaborating junior professor, Josef Grabacha. All right, let's jump right in. So AutoML, there is decades of work on predecessors of our systems that I will talk about. In particular, there's been European projects since the 90s. There's been lots of work, of course, on hyperparameter optimization over the decades. There's been lots of work on model selection already in the 90s. And some sort of automation methods have been used for decades. For example, WEKA had grid search and scikit-learn already has grid search and random search. RapidMiner had grid search in the 90s already. So there's lots of work that happened before our work. But arguably the first real push button AutoML system that I'm aware of is this Auto-WEKA system that we did in 2013. So that's now 8 years ago already. And since then, AutoML has really grown to become quite a subfield of its own of machine learning. So in Auto-WEKA, we built this around the WEKA system in Java that has 27 base classifiers, 10 meta methods, 2 ensemble methods, in total something like 786 hyperparameters. And this is a ridiculous number, seeing that WEKA is meant for, really meant for mostly novices trying to use this in their daily life, trying to use machine learning. And well, Many of them would just use some classifier, for example, an SVM, because a friend told them it works well, with default parameters because they don't know better, because they're not machine learning experts. And that's problematic because, of course, SVMs don't necessarily work very well with default hyperparameters because they need to be tuned. So that's why we came up with Auto-WEKA in order to really come up with a one-stop system that actually does this optimization automatically. So by doing a search over the space of 786 hyperparameters, in particular using Bayesian optimization with random forest by this SMAC algorithm here. And notice that we optimized cross-validation performance. The cross-validation performance is actually defined as a sum or an average over the performance of the individual folds. So if our individual classifiers are actually expensive to train, we have this expensive big black box function, then actually this sums as a sum of smaller black box functions, and we can use this. We can get speed ups by actually only evaluating single folds at a time and stopping once some of the folds perform really poorly. And so this Auto-WEKA system then actually already performed better than each base classifier inside of WEKA. I don't want to speak much more about WEKA other than saying it's actually still used quite a bit. Now I want to go to Auto-sklearn, which is used much more frequently in the current machine learning sphere, where it's much more focused around Python than Java. And scikit-learn is, of course, an extremely popular package for machine learning. Now, here we optimize cross-validation performance over only 110 different hyperparameters in order to actually be more efficient. And we also use meta-learning across datasets in order to warm start the Bayesian optimization and initialize the model with good configurations from similar datasets. And that allowed us to speed up the search a lot from the previous 2 days of Auto-WEKA to something around an hour for Auto-sklearn. Also, what we did here is to use automated post-hoc ensemble construction to combine the models that Bayesian optimization has already evaluated anyway. So we get ensembling for free. We already have all these models evaluated. We just need to spit out a combination of these models. And so that efficiently reuses the data we have gathered already and improves robustness over only returning a single model. Now, Auto-sklearn did actually win this first try-learn AutoML challenge that was over the course of 16 months, 2015 to 2016, now already a while ago. And that's why I don't want to talk more about Auto-sklearn as such, other than saying, well, it is a popular open source framework, but I want to talk about its successor, Auto-sklearn 2. And well, Auto-sklearn 2 compared to Auto-sklearn 1 makes a series of improvements. So I will talk about these improvements in turn. The first one is just simple practical considerations. So one issue in AutoML is that, well, you want a system that works off the shelf and just gives you good performance. And if you have some models that would actually take for a long time because the data is just large and they would run, for example, for a day, and you only have a budget of an hour, then, or even if you have a budget of a day, this single run would just take all your budget and you wouldn't progress. So what you really need to do is terminate long algorithm runs early. And Auto-sklearn 1 already, of course, did terminate them, but it counted them as unsuccessful. And what we do now in Auto-sklearn 2 is a really simple thing, but it's important, namely saving the intermittent results of iterative algorithms. If we have tree-based methods and we have fit, say, 7 of 10 trees, then we still save the performance of these 7 trees. Or if we have run 17 epochs of SGD, but not the 50 that we wanted to run, we still save the partial model. And this is very important, particularly for large data sets. So in this plot here, we have the runtime in seconds on the x-axis, and on the y-axis, we have the balanced error rate. And we see that on average, that's this bold line here, The orange, which is with our intermittent results retrieval, is much better than the green. And especially for the dashed line, this is for the large data sets, the difference is particularly large, and it's also particularly large in the beginning when you have relatively low runtimes. All right, so that's a practical improvement, and that's important. Another practical improvement is that, well, 110 hyperparameters that we had in Auto-sklearn 1 is actually still a lot. The newest version even has 153. And in Auto-sklearn 2, we rather reduced the search space to only have 42 hyperparameters, and in particular focus only on iterative methods to support this intermittent results saving and also multi-fidelity optimization that I will talk about later. So this substantially reduced, well, not this, but we also substantially reduced our pre-processing options. And this was particularly important again for the large datasets because it saves us just time and lets us make progress in the allowed time much faster. All right, so those were just engineering considerations, albeit important, but let's now talk about some researchy advanced. So the first improvement is multi-fidelity optimization. Now, a brief overview of multi-fidelity optimization. The key idea is as follows. So we want to use cheap approximations of an expensive black box function. And these cheap approximations should have the property that performance on them should correlate with the performance of the black box. Some examples of this could include, for example, using a subset of the data, using fewer epochs of iterative training algorithms such as SGD, using downsampled images in object recognition. If you do Bayesian deep learning, short MCMC chains. If you do deep reinforcement learning, fewer trials. Here in Auto-sklearn 2, we use less trees in tree-based models and less epochs in SGD. And so the simplest method you can think of there is successive halving by Jamieson and Talbakar, which basically just says you have these different fidelities. After a given fidelity, for example, here wall clock time, you just look at the performance of all your different hyperparameter settings, terminate the poor ones, let the better ones continue and iterate, and you double the budget and half the number of runs. Again, after the double budget, you terminate half and double the budget, you terminate half and double the budget. And this already gives you a very, very nice trade-off of being able to put a lot of resource into the good runs and not wasting too much time with the poor runs. There's many more complex methods, and in fact, the combination of the successive halving method and Bayesian optimization, well, actually of hyperband and Bayesian optimization in Bob shows much better convergence because, well, successive halving is just based on random search and doesn't find the best elements in big configuration spaces. Now, the results of this are, again, that it mostly helps for large data sets and also for short runtimes. So for short runtimes here, you see quite a big difference between using the successive halving and using holdout. Good, moving to the next improvement. This is portfolio construction, and basically this is for meta-learning across data sets, which has improved in Auto-sklearn 2. So the main idea, just to remind you, we want to transfer information from previous runs on previous data sets. And as a reminder, Auto-sklearn 1's approach is as follows. So we have a bunch of different meta features, in particular 38, some of them fairly complex. And based on them, we selected 25 different data sets from our metadata that are similar to the new data set that we want to tackle based on these meta features. And then we initialize the optimization by running these 25 configurations on our new data set. Now, this has several problems. These 38 meta features we actually need to compute on our new data set, and that can be actually expensive and might be very hard to do in a constrained time. And if a meta feature computation, for example, takes an hour, then it's very hard to terminate that and deal with the fact that you have terminated it. And yeah, also well, there's added complexity of the code of computing these meta features, of policing the time and the memory for this meta feature computation. Think about AutoML systems, right? You need to be robust, and this just needs to work off the bat every single time. Many of these meta features are also not defined for categorical data, or if you have missing values, etc. And you might actually select redundant pipelines. So if there's 25 data sets that look quite similar to yours, and well, the types of methods on there that work well are similar or even identical, well, you will just pick similar or even identical pipelines in these 25 initialization pipelines. And that's, of course, not what you want to do. You want to have complementarity in those runs. So what this portfolio construction is about, it tries to find a set of possible machine learning pipelines and given a set of possible machine learning pipelines, and given the matrix of how well does each of these pipelines work on each of these data sets, you want to actually find a portfolio that is a subset of possible machine learning pipelines such that you minimize the oracle loss. So the oracle loss is defined as follows. You just sum over your data sets, and for each data set, you get to pick the best portfolio member in your the best element of your portfolio. And so that's what you want to minimize. Now, this is just the same equation again. And the greedy function optimization then says we start with an empty portfolio of machine learning pipelines and iteratively add to pipeline little p that marginally reduces this oracle loss most. So it's a very simple approach that just looks through your possible portfolio members and says, okay, now I'm going to add this one because that helps most on average on top of what I already have across my set of meta data sets. And the use of this approach is not new. Actually, Martin Wistuba already used this in 2015, but he used it as a heuristic without theory. And so we actually have some theory for this. We have a proposition that the portfolio construction problem is actually equivalent to the sensor placement problem for minimizing detection time. And because there is lots of theory for that problem, we have a bunch of corollaries. One is that our penalty function is actually submodular and monotone, and finding an optimal portfolio is NP hard. We also know that the greedy algorithm has a regret that is a 1 minus 1 over E approximation. And we also know that compared to the regret of the optimal portfolio of size K, if we allow 5K algorithms, then the greedy algorithm's regret is upper bounded by just 1% more regret than this optimal portfolio with K elements. And we can also apply other strategies for sensor set placement, such as any algorithm for solving NP-hard problems, mixed integer programming, for example, which can yield optimal results for small problems, but for large problems doesn't scale. Now, in terms of empirical results, this portfolio construction yields a clear improvement over Bayesian optimization from scratch. It doesn't improve much over this previous approach that's based on a k-nearest data set from Auto-sklearn 1, but it's much simpler and easier to maintain, and it has theoretical worst-case guarantees. And based on these 3 improvements that I mentioned so far, we actually also won the second AutoML challenge that was from 2017 to 2018. Now moving on to the third improvement, automated policy selection. So one problem is that there is no single best model evaluation strategy. It's not always the case that holdout is better than 3-fold cross-validation or 5-fold is better than 10-fold. It's also not the case that successive halving is always better than holdout. So here are some examples on different data sets, on the Robert data set and the Faber data set. On this one here, it's clear that holdout is better than 3-fold, is better than 5-fold, is better than 10-fold. And successive halving doesn't really help. It makes things a little bit worse over not using successive halving. In contrast, on this data set here, 3-fold without successive halving is actually better than holdout or 5-fold or 10-fold, and successive halving tends to also help quite a bit. So across different data sets, you don't always have the single best model evaluation strategy, but even across time budgets on the same data set. So here we have a data set for 10 minutes and the same data sets for 60 minutes. And for 10 minutes, you want to do successive halving with holdout, but that is actually amongst the worst strategies if you have 60 minutes of runtime. There you can afford 3-fold cross-validation. And if you were to give it more time, you could probably afford 10-fold cross-validation. So there is, you want to actually look at your data set and at your budget in order to decide which model evaluation strategy to use. And we will do this actually based on really simple meta features. We dropped meta features before, but now we really use very simple meta features. Just the number of data points, number of features, number of classes, which you can just look up in milliseconds, and there's no issue of memory consumption, etc. We do not use these 25 previous complex meta features of Auto-sklearn 1. All right, so in principle, this is actually a direct application of the algorithm selection problem from Rice in 1976, where you basically map from the budget and meta features to the best model evaluation strategy. And we can use standard approaches such as cost-sensitive random forests. One problem is that the optimized portfolio also depends on the model evaluation strategy because, well, the greedy algorithm selects the machine learning pipelines that work best if you use a particular model evaluation strategy, such as 5-fold CV. We can have a simple solution for this, though. Basically, for each of the model evaluation strategies we consider, and there's only 8 of them, we basically pre-compute what our optimized portfolio would be. And the portfolio of machine pipelines that we would use if we use successive halving might be very different than what we use if we use 10-fold cross-validation without successive halving. And this way, for each data set, we actually get a score for each model evaluation strategy and can directly apply algorithm selection. One technicality is here that we need to do an additional inner cross-validation, but yeah, that can be done. Okay, so in terms of results, the selector clearly works better than using the single best model evaluation strategy. So within 10 minutes, we get a normalized error of 3.09, which is actually better than the single best would do in an hour. So that's quite nice. And also, if you do a rank-based analysis rather than this analysis based on normalized error, the selector also has the best overall ranks. Now putting it all together in Auto-sklearn 2. How does this all work? So in orange, we basically have user inputs. We need a set of representative data sets. So the user needs to decide, I want to tackle data sets like X, and then I choose my metadata sets that are somewhat representative of this new data sets, the new types of data sets. And the user also needs to decide on some, no, actually the meta features we decide. So we then obtain a set of candidate machine learning pipelines on these data sets, for example, by just running SMAC offline on them. We then evaluate each single pipeline on each single data set in order to get basically a performance matrix that tells us how well each pipeline does on each of the data sets. And then we build our policies for each of the different model evaluation strategies. We compute meta features and train our selector based on how well, based on the entries of this performance matrix. Then at test time, given a new data set, we compute meta features on the training split of the new data. We apply our algorithm selector to choose our policies, our model evaluation strategy, and our portfolio. Then we apply it to the training data and, well, output some performance or make predictions on the test split. And we can, of course, also assemble different pipelines. All right, this probably for offline. How do all these different improvements correspond to these different boxes? You can look that up offline in the slides. More importantly, comparing Auto-sklearn 2 against 1. So we clearly have a quite big improvement. So the average regrets actually are, we have a 5-fold reduction of them. And Auto-sklearn 2 does much better in 10 minutes than Auto-sklearn 1 does in even 1 hour and longer. In terms of ranks, Auto-sklearn 2 also does better than Auto-sklearn 1 and various other ablations. All right, so this was all I wanted to say for Auto-sklearn 2. It's in the same repo as Auto-sklearn 1. And yeah, I encourage you to use it and send us feedback. Next, I want to talk about Auto-PyTorch Tabular. Here we're only going to use a subset of improvements, and I'm going to go through them very quickly because it's the same improvements as for Auto-sklearn, really. So we have practical considerations, we have multi-fidelity optimization, and portfolio constructions. So we have the system Auto-PyTorch that actually historically, we already in 2015 were developing a system called AutoNet. And well, it wasn't PyTorch back then, but it was also meta-level learning and optimization on top of deep neural networks. And it was actually the first time that, to the best of my knowledge, an automated machine learning system actually won against human experts in a competition based on several data sets. So for example, this competition with around 55,000 data points, 5,000 features. This AutoNet actually got a performance score of 0.9, whereas many different teams of human experts, given 2 months, actually couldn't get to the same performance. And yeah, Auto-PyTorch is the successor of this. It has a pretty simple space. We actually only use feed-forward neural networks here, ResNets with some skip connections. And there is something like a dozen of architectural hyperparameters and a dozen of hyperparameters for the training pipeline. In terms of multi-fidelity optimization, we again use Bob and yeah, see nice speedups for large data sets and small runtimes, just like for Auto-sklearn 2. We also use the same portfolio construction without meta features and see sometimes 100-fold speedups using that over actually doing the optimization on the new data set directly. And this leads to very nice performance compared to other previous AutoML frameworks, such as AutoKeras, also the Auto-sklearn 1 and HyperOptaScaling. The methods underlying Auto-PyTorch and Auto-sklearn 2 also can actually work well for image data. So, and in particular for neural architecture search. So NASBench 201 is a neural architecture search benchmark that has in there CIFAR 10, CIFAR 100, and a downsampled version of ImageNet. And we can apply the same meta-learning approach based on really just having 2 meta-trained data sets, because we only have 3 available here in this data. But this actually also already yields speedups of something like a factor of an order of magnitude or even 2 orders of magnitude sometimes. The multi-fidelity part does not help in this particular case because in NASBench 201, there's actually weak correlations across the budgets. So when you only do a few epochs, then that performance doesn't actually correlate too well with the performance you would get with longer runs. But warm starting helps a lot. And it helps so much that actually this is 4 times faster than gradient-based neural architecture search, such as DARTs, etc., to obtain 90% performance on CIFAR 10. All right, the final thing I want to talk about is sort of towards the future of Auto-sklearn, of Auto-PyTorch, Tabular. It's based on Auto-PyTorch, and it's about improving deep learning for tabular data by more regularization. In particular, there we studied 13 different regularization methods and their subsidiary hyperparameters and optimized them on a per dataset basis. And here's a list of these different 13 types of regularizers. And surprisingly, this really simple approach of just looking at multiple regularizers and the right mixture of them, the right cocktail, actually already yields new state-of-the-art performance, a new state-of-the-art model for tabular data, even when you only use simple multi-layer perceptrons. There's no need for a particular type of architecture. Already with this here, it works really well, and this could, of course, potentially be combined with other novel architectures for deep learning for tabular data. And so the baselines we used are different modern types of deep learning methods for tabular data, such as Google's TabNet, or these neural oblivious decision ensembles, and also Auto-WEKA based on neural networks. And we also compared to traditional machine learning methods, in particular, the very popular method of gradient boosting in 2 versions. So we looked at the version in XGBoost, and we also looked at Auto-sklearn with just gradient boosting. Those 2 were extremely similar. They're these 2. So both of these are gradient boosting. Tabnet and Node were not so good in these experiments, and Auto-WEKA with neural networks was quite good. But still, just a simple machine modular perceptron plus our cocktails perform substantially better and significantly better. So here's a more close evaluation of these on 40 different data sets. So the cocktails against different types of methods. So for example, against the standard MLP, we had 35 wins and 5 losses. Against XGB, we had 26 wins and 12 losses and 2 ties. Against Tabnet, 38 wins and 2 ties. And here's a scatter plots against the best competitors. So in particular, against Auto-WEKA, it typically improves performance. Against XGB, it typically improves performance. There is still cases where it performs worse, but overall, statistically significantly, it performs better. To put all cards on the table, there are some limitations here. These are clean data sets, they're quite balanced, there's no bad outliers, so it's still a nice protocol, and there's still a lot of work needed in order to scale this up and deal with dirty data. And so far, it's quite slow. We have simple runtime limits of 4 days on a single machine. There's no meta learning yet, and this could probably speed this up a lot. All right, so to conclude, I've talked about the evolution of our AutoML systems, Auto-WEKA, Auto-sklearn 1, Auto-sklearn 2, and Auto-PyTorch. The main speedup techniques were practical considerations, multi-fidelity optimization, greedy submodular portfolio construction, and automated policy selection. Right, with that, I would like to thank you for your attention.